For my project, I studied an optomechanical detection technique which could be used to search for SU particles clustered into boson stars. As it stands currently, there is significant evidence for the existence of dark matter, though no specific particle has been detected yet. In recent years, the focus of dark matter research has shifted to ultralight and axion-like candidates, since heavier candidates have not been detected. One particular detection technique which could search for ultralight dark matter candidates is optomechanical force sensing. Essentially, optomechanical force sensing just uses a mechanical force sensor coupled to an interferometer so that when a dark matter wave hits the sensor, it causes the sensor to move, leading to a phase shift in an optical cavity, which we can detect using this interferometer. Previous work has shown that this type of detector offers many advantages for detecting dark matter in diffuse fields, especially when scaled into an array. To determine the force on this sensor due to an ALP, we assume that ALPs interact with the standard model via Yukawa coupling to neutrons, which has the effect of modulating the mass of the particle. As the boson star moves across the center of mass of the sensor shifts towards the boson star's center of mass, causing the sensor to move. Formally, we assume that coupling is of the form shown here, where y is a coupling constant, and we assume that the dark matter field in the non-relativistic limit is of the form shown here. Since the Grossz-Piketty equation describing the star is Galilean invariant, the field psi must obey this transformation law. And then the above equations imply that the dark matter field describing the star is of the form shown here. By noticing that the coupling term behaves like a mass term in the direct differential, we determine the force on the sensor due to an ALP is of the form shown here. To model the boson stars, we assume that they can be described using an energy functional of the form shown here, where Vg is the gravitational self-interaction determined by the Boson equation, and lambda is the self-interaction between the bosons. To determine the wave function, we use a variational technique with a variational on top of the form shown here, and then minimizing the energy functional with respect to sigma d allows us to determine this value for sigma d, which we substitute back into our variational on top, which gives us our approximation for the wave function. And then, once we have our approximate wave function, we can evaluate for the central density, which is given by this equation here. And then, to verify that this estimate for dark matter density is consistent with observational results, we compare the density of the boson star onslaught with some observational upper limits on the matter density in our solar system. And then we can determine that the upper limit on boson star density for a boson star centered around the sun at the Earth is approximately equal to 5 × 10⁴ GeV per centimeter cubed, compared to a diffuse dark matter field with density equal to the local dark matter density of 0.3 GeV per centimeter cubed. A boson star centered around the sun has a much higher density, and since the force on the sensor is proportional to the square root of the dark matter density, this leads us to hypothesize that the signal that we could expect for this scenario would be much higher than for a diffuse field. To determine the collision rate for a star coming from outside our solar system, we assume that collision cross-section is of the form shown here, where r target is equal to the radius of the Earth, and r99 is equal to the radius in which 99% of the matter in the boson star is contained. And then if mean free path is equal to this equation, and number density is equal to this equation, you can determine the collision frequency, which is equal to the following. And then we can rewrite the collision frequency in terms of the density of the boson star. The observed helium abundance constrains allowable coupling values. If we assume that the neutron to proton ratio is given by this equation here, where Q is the neutron proton mass difference, and then the change in the neutron proton mass difference due to ALP coupling to the standard model is given by this equation, and the mass fraction of helium is given by this equation, we can determine the change in mass fraction due to an additional particle coupling to the standard model is given by this equation here. And then, since helium abundance is measured in 10% accuracy, we can determine a numerical constraint on coupling is equal to this equation here, where mass is measured in EG. And then we can also look at how fifth force experiments constrain helium coupling to the standard model. And what we find is that throughout the parameter space we are looking at, fifth force experiments actually place tighter constraints on coupling than BBN. And then As you can see in the plot shown here, this blue region represents the constraints from fifth force experiment, so coupling and mass values which have already been ruled out, and then this red line represents the smallest observable coupling and mass values we could observe for a particular density of boson stars. So what you can see in this plot is this white space in between the red line and the blue line represents the parameter space, which is observable using this experiment, but which has not yet been studied by other fixed force experiments. So this leads us to conclude that optomechanical sensing could be used to search for bosonic dark matter in boson stars. To finalize the calculations in this project, we still need to determine the possible signal we could detect and finish scaling over the entire available parameter space to determine detection rate.